Manual transmission in automotive vehicles. This is an essential part of every combustion engine vehicle, from the standard family car to the highly tuned sports car. So, how does it work and why do we need it? That's what we'll be covering in this video, which is sponsored by the Great Courses Plus. Visit the link in the video description to start a free trial and get access to some truly great online courses. In every rear-wheel drive combustion engine vehicle, we find the following parts: the engine, clutch, transmission, drive shaft, differential, axle, and wheels. Front-wheel drive and four-wheel drive vehicles are slightly different, but they all require a transmission. The engine combusts fuel, which moves the pistons and crankshaft, creating rotation. The clutch engages or disengages the engine's rotational energy to the transmission. The transmission contains a number of gears, which transfer the power of the engine towards the wheels and enables us to change the speed and the torque of the vehicle. The shaft transfers the power to the rear differential. The rear differential distributes this power to the wheels, causing them to rotate and propel the car along. Manual transmission requires the driver to know exactly when to change gear, which gear to change to, and also operate the clutch pedal to disengage and then re-engage the engine. We can also get automatic transmission vehicles, which will automatically do all of this for us. The driver simply needs to put the vehicle into drive, and the car will take care of the rest. By the way, you can download a personal copy of this video and help support the channel. I'll leave a link in the video description down below if you would like a copy. Which do you think is better and why? Manual or automatic? Let me know your thoughts in the comment section down below. If you have ever ridden a bike, you'll know it's very difficult to start pedaling in a high gear. So we need to start in a low gear to get the bike moving. At a certain point, our legs are spinning very fast, but we can't go any faster. So we need to change to another, higher gear. Once we reach a steep hill, we need to move to a lower gear. The same with a car. We start in our lowest gear number and work our way up as the vehicle increases in speed. Then we change down as we drive up a hill. A low gear provides low speed but high torque. A high gear gives high speed but low torque. Torque is a measurement of the force which causes something to rotate around a point. Think of a wrench and a nut which has seized up. Using a small wrench is very hard to free the nut. Using a long wrench will make it much easier. That's because of torque. If we used a 30 centimeter wrench and applied 90 newtons of force, we have 0.3 meters multiplied by 90 newtons, which gives us 27 newton meters of torque. However, if we applied the same 90 newtons of force to a wrench that was 60 centimeters long, then we would get 0.6 meters multiplied by 90 newtons, which gives us 54 newton meters. So from this simple formula, you can see we have more force acting on the nut by using a longer wrench. We're using a larger circle to turn a smaller circle. By changing the size, we change the speed and the torque. If we were to connect two gears and rotate one of them, then the other gear would also rotate. If we attach the engine to the first gear, then this will be the driver gear, and the other gear is therefore the driven gear. When the two gears are the same diameter, we have a 1-to-1 ratio, which means every time the driver gear completes a full rotation, the driven gear also completes one rotation. So the output speed is the same as the input speed. If the driven gear is half the diameter of the driver gear, then we have a 1-to-2 ratio, which means for every full rotation of the driver gear, the driven gear completes 2 full rotations. This means the driven gear is rotating much faster. If the driven gear is twice the diameter of the driver gear, then we have a 2-to-1 ratio, which means for every 1 full rotation of the driver gear, the driven gear rotates only half a turn. So we need the driver gear to rotate twice to complete a full rotation of the driven gear. Notice that the driven gear rotates the opposite way. This is basically a reverse gear. In order to make the output rotate in the same direction as the input, we need to insert another gear which creates something known as a gear train. The middle gear is known as an idler gear. We could add many gears side by side to change the speed and also the output direction, but this will take up a lot of room. So instead, we can mount gears to the same axis and create a compound gear train. This will do the same job, but it will take up far less space. We'll look at how to calculate gear speeds, ratios, and sizes towards the end of the video. First of all, we have the main housing. This will protect all the internal components and hold them in place. Looking inside, we have the input shaft, the output shaft, and a counter shaft. A number of gears are fixed to the counter shaft. These will therefore all rotate together. On the input shaft, we also have a gear which is in constant mesh with the counter shaft. The gear teeth are at an angle, which is known as a helical cut. These gear teeth gradually engage on multiple teeth, from one side to the other. This distributes the stress on the gears and makes the gear mesh much quieter than a straight cut spur gear. At the other end of the input shaft is the clutch. This will connect to the engine and force the input shaft to rotate. Anytime the clutch is engaged with the engine, it causes the input and counter shaft to rotate. There are also a number of different size gears on the output shaft. These are also in constant mesh with the gears on the counter shaft, and so when the counter shaft rotates, so will the output gears. However, notice that the output shaft does not rotate with the output gears. That's because each output gear sits on a needle bearing. This allows the gear to rotate independently from the shaft. If we look at the output shaft, we see there are a number of spline sections. These are grooves which are cut into the metal. A synchronizer hub fits over the splines. The splines will lock the hub in place so that it will rotate with the shaft. Another component called the synchronizer sleeve will fit over the hub. The outer surface of the hub and the inner surface of the sleeve are both splined. This interlocks the two components. The sleeve can move forwards and backwards on the hub. When the output shaft rotates, so will the hub and the sleeve, but not the output gears. Attached to the channel, on the outside of each of the sleeves, is a shift fork and a shift rod. The rod connects to the gear shifter. The gear shifter moves the rod backwards and forwards, which therefore also moves the fork and sleeve backwards and forwards. On each of the output gears, we find some additional straight cut teeth. These teeth will align with the spline teeth inside the sleeve. When the gear is selected, the teeth inside the sleeve align and interlock with the straight cut teeth on the gear. The gear will now be interlocked with the sleeve and the output shaft. So, when the input shaft rotates, this rotates the counter shaft, which rotates the output gear, and this now rotates the output shaft. When the gear is disengaged, the sleeve returns to its default position, allowing the output gear and the sleeve to rotate independently from each other. The problem we face is that the output shaft and the sleeve are rotating at different speeds to the output gear. So, when we engage the sleeve, the teeth are going to collide and grind. To overcome this, we use a synchronizer blocker ring. It's called this because it will prevent or block the gear from changing until the sleeve and the gear speed are synchronized. The inner edge of the blocker ring is angled and matches the cone on the gear. This allows the blocker ring to easily slide on and off of the gear. We also have some small struts which are inserted into the slots of the hub. These are held in place by a radial spring which pushes them outwards. The sleeve sits over the struts and the hub. A ridge on top of the strut interlocks with the sleeve. The sleeve will move the struts back and forth. There are also some slots cut into the blocker ring. These will align with the struts. The slots are wider than the strut, which allows the blocker ring to rock back and forth a small amount. The blocker ring rotates with the hub and the sleeve. When a gear is selected, the sleeve moves towards the gear. This pushes the strut against the blocker ring. The blocker ring rubs against the cone of the gear, causing the blocker ring to rotate until it hits the limit of the slot. The blocker ring's teeth and the sleeve teeth are now out of alignment. This prevents the sleeve from engaging with the gear. As the blocker ring continues to be pushed against the gear cone, the friction generated between the two causes them to synchronize speed and rotate together. The sleeve is then pushed across, moving the blocker ring and allowing the teeth on the sleeve to engage with the straight teeth of the gear. The gear is now synchronized and the clutch can be engaged. To reverse the car, we need to bring the car to a complete stop. An idler gear is then pushed into position with both the output and the counter gear. All three gears are straight cut, which is also known as a spur gear. The idler gear is free to rotate. This allows it to slide into position when the car has stopped. Now the output shaft will rotate in the opposite direction. The engine is going to provide the rotational energy. If we engage the clutch with the car in neutral, the input shaft rotates, causing the counter shaft and the output gears to rotate. The output shaft does not rotate though. For first gear, we disengage the clutch, which stops the engine from adding any further power to the input shaft. Then we push the gear stick so that it moves the sleeve. The blocker ring rubs against the gear hub and uses the friction to synchronize the speed. Once synchronized, the sleeve moves across to interlock the gear to the output shaft. For second gear, we disengage the clutch and use the gear shifter to disengage the first gear sleeve. Then we move the shifter into the second gear, which pushes the sleeve and blocker ring. This synchronizes the speed and interlocks the second gear. For third gear, we disengage the clutch and use the gear shifter to disengage the second gear sleeve. Then we move the shifter into the third gear, which pushes the sleeve and blocker ring. This synchronizes the speed and interlocks the third gear. For fourth gear, we disengage the clutch and use the gear shifter to disengage the third gear sleeve. Then we move the shifter into the fourth gear, which pushes the sleeve and the blocker ring. This synchronizes the speed and interlocks the fourth gear. For fifth gear, we disengage the clutch and use the gear shifter to disengage the fourth gear sleeve. Then we move the shifter into the fifth gear, which pushes the sleeve and blocker ring. This synchronizes the speed and interlocks the fifth gear. For reverse, we bring the car to a complete stop and disengage the clutch. All of the shafts and the gears come to a stop. We then slide the idler spur gear between the counter and the output gears. Then we re-engage the clutch to reverse the direction of the output shaft. So this is how we use the engine to propel the car along and use gears to go faster. And if you are ready to step up a gear, then you should check out the Great Courses Plus. All of our viewers can get a free trial right now by visiting thegreatcoursesplus.com/engineering mindset. The Great Courses Plus is an on-demand learning platform that lets you binge watch lectures and courses. They have over 13,000 videos by industry experts on everything from science, maths, history, and even cooking. Personally, my favorite is their engineering lectures and their course on inventions that change the world. As a fan of this channel, I'm certain you'll also find these interesting too, so do check those out. They add new content every month, and you can watch as many videos as you want from your TV, tablet, laptop, or phone. Just click the link in the video description down below to start your free trial today. Let's look at how to calculate the RPM and torque of simple gear trains. By the way, you can download an Excel sheet of these calculations. Links can be found in the video description for those. We're going to use the formulas ratio equals teeth of the output gear divided by teeth of the input gear. RPM output equals the RPM input divided by the ratio. And finally, torque output equals the ratio multiplied by the torque input. For example, if gear A has 8 teeth and gear B has 10 teeth, the ratio is 10 divided by 8, which is 1.25. If gear A rotates at 150 RPM, then 150 divided by 1.25 equals 120 RPM. If gear A has a torque of 20 Newton meters, then 1.25 multiplied by 20 gives us 25 Newton meters. This gear will rotate the opposite way to gear A. It will rotate slower because it is larger, but it will have more torque. If we add gear C with 20 teeth, the ratio is 20 divided by 10, which gives us 2. The RPM output is 120 RPM from gear B divided by 2, which gives us 60 RPM. The torque is going to be 2 multiplied by 25 Newton meters from gear B. This will give us 50 Newton meters. So this gear will rotate the same direction as gear A, but it will rotate slower because it is larger, although it will have more torque. If we were to add gear D with 8 teeth, then the ratio is 8 divided by 20, which gives us 0.4. The RPM is 60 RPM from gear C divided by the ratio of 0.4, which gives us 150 RPM. The torque is 0.4 multiplied by 50 Newton meters, which gives us 20 Newton meters. So this gear will rotate the opposite way to gear A, but it is the same size, so it will rotate at the same speed and the same torque, although this doesn't take into account any losses which we would see in the real world. So this setup lets you visualize how gears manipulate speed, torque, and direction. What if we had a compound gear train like this, which has the same size gears, the same input torque, and the same rotational speed? Again, links in the video description for the Excel sheet calculator for this. So with this setup, we have 4 gears, A, B, C, and D, but B and C are compound. If gear A has 8 teeth and gear B has 10 teeth, then the ratio is 10 divided by 8, which is 1.25. Gear A rotates at 150 RPM, so gear B is 150 RPM divided by 1.25, which gives us 120 RPM. Gear A has a torque of 20 Newton meters, so gear B is 1.25 multiplied by 20 Newton meters, which is 25 Newton meters. So this gear rotates the opposite way to gear A. It will rotate slower because it is larger, but it has more torque. If gear C has 20 teeth, then the ratio is 20 divided by 10, which is 2. The RPM is going to be the same as B, which is 120 RPM, because these two gears are compound and share the same shaft. The torque is also going to be the same as B, so it's 25 Newton meters. This gear also rotates the opposite direction to gear A. It will rotate slower than gear A because of the size of gear B, and it will also have less torque than gear A, again because of gear B. If gear D has 8 teeth, then the ratio is 8 divided by 20, which is 0.4. The RPM is 120 RPM from gear C divided by 0.4, which is 300 RPM. The torque is 0.4 multiplied by 25 Newton meters from gear C, which equals 10 Newton meters. So this gear rotates the same direction as gear A. It rotates faster, but with less torque. So we need to consider the application of the gearbox, how many gears are connected, and what torque and speed we require. Okay, that's it for this video, but to continue learning about mechanical and automotive engineering, check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, as well as theengineeringmindset.com.